I started
Okay.
recording.
So it is my pleasure to introduce today's speaker. It is Oleg Musin from University of Texas, Rio Grande Valley. And so Oleg will tell us about majorization, discrete energy on spheres, and F designs. So as usual, after the talk, there'll be some time to discuss it and for some informal conversations. So Oleg, please.
Okay, thank you very much for this invitation. And I was between three different talks when I was thinking about it. I decided to present, discuss today majorization. I will explain soon what it is. Actually, it's my third one. It is a third attempt to discuss this topic. One, it was 1 year ago, more than 1 year ago. And this, we have a section in Denver. But there only I have 20 minutes. And after that, I changed, maybe this paper was changed. I submitted it to the journal. I don't remember, also maybe not January, maybe 1 year ago. I remember. It's about that. And after that, reviewer, thank you very much. I don't know who reviewer, they sent me one. It was like 5 pages or 6 pages. Like it was paper like 12, 15 pages, but they sent me like 6 pages and another one like 3 pages. Suggestions, very, very useful. Very. I spent next 3 months, to make changes. And especially I'm improved for the last part about F designs. At my second presentation, here we have at least 3 participants who already participated conference. It's called Geometric and Combinatorics Day in MIPT at the Moscow Institute of Physical Institute. It was conference in the beginning of December, but I had no time to discuss. This maybe most interesting part right now for me to time F design. Not because I have 15 minutes and spent a lot of time for the presentation for the beginning. But today I try to have at least 10-15 minutes to discuss like that part. Right, because in there, yeah. Okay, now I'm going to discuss. We'll discuss this majorization. Let me just briefly discuss definitions. Briefly discuss definitions. Majorization, actually, it is, I don't know when it is first defined, probably maybe about 100 years ago, because of this. It is actually one of it is also we can find in the one of about inequalities okay. Anyway, let us consider any segments of real numbers and numbers, and to consider permutation and consider permutation in increasing order. That means, we have a sub 1 and a sub, so a sub n is increasing order. And we can compare both 2 sequences of the same length. Then we say that A majorizes B, and denoted by this symbol, that means A majorizes B, if for any k between 1 and n, we have this inequality. A sub 1 plus A sub k is greater than the same sequence of B. Yeah, that means, the minimum, if you have A and B, right, that the minimum, of course, it has to be greater or equal to B, and so on. But in the first, the minimum, and the next one, it also has to be greater or equal to B. But of course, not all comparable. There are incomparable, actually, sequences. So we have 2 possibilities. It can be majorizers, and sometimes it can be incomparable. There is a classical book. I don't know how published. Just when it's published, maybe also old one. I know that there exist also some new the Marshall-Olkin is called Inequality Theory on Modularization and Application. There's a nice book. Yeah, but in this book, by the way, it is called weak modularization. Weak modularization, the reason is because they consider it always when sum of A equals is equal to sum of B, right? I mean, they have equality. In this case, we have a modularization. We have that. The reason is, I'm explaining. The reason is because it is also the same. I'm not agree, by the way, with the word weak, but it is different, a little bit more different. Let us consider the first example that we are very old, namely Jensen inequality. Jensen inequality says the following thing. Let us consider mean value for a given sequence A. Mean value denoted by A bar, right? And let a capital A bar, it is like consists of a mean value. In this case, we definitely have that a bar is modularizes A. This is obvious, right? Yeah. Moreover, okay, here we have equality. We have equality, right? Because in there we have A and a bar. We have sum of elements. It is sum of this a bar. You know, it is equal. We have equality. But what is not, we have no equality. Consider any S greater or equal to a bar. In this case, we have also modularization because we have this obvious. We have obvious modularization. This one as well like the next one. So actually, it is from this follows from this. I mean, from this one and from this one, we have actually. Yeah, that implies two Jensen inequality. Usually, both consider it in. We consider it in different. I mean, this very useful. The first Jensen inequality says that if you have then let f be just convex function, any convex function, real convex function, then f of a1 plus and so on, the sum of f of ai divided the mean value is greater than f of mean a bar. I mean the mean value of a. This is a convex function. And Jensen inequality 2 that I told you that some people call this weak. I don't know why it's weak. It is different. It's another. Suppose we have any s when s is greater than equal than the average, right? In this case, we have that the mean value of fi divided by f. But in this case, f has to be convex and decreasing function. Not only convex and also convex and decreasing function. Yeah. There is also version also for increasing function, but this is for decreasing function. In this case, average of f of I is mean value of f of 1, so it's a mean value, it's greater than f of s. It is not true for the case just only convex. You can imagine that because in convex can be also increasing. And in this case, it doesn't work. So it is, I don't know why it's called, people call this weak, but however, weak because we have also some additional assumption. It's about decreasing. So I don't know how many Jensen inequality are very old. Came from, I don't know, from 19th century, from 18th century. And it's about 100 years ago appeared the modularization inequality that it also independently it was actually found by Karamat. Sometimes some people call this Karamat inequality. Yeah, and this says the following. exactly using my notation. I'm going to discuss today only weak version. In I mean, that's what people call weak. Suppose we have f can be any convex. I mean, like that is generalized the generalized inequality 2. Let f be convex decreasing function, and suppose a majorizes b. Then f of a1 so on plus fn is less or equal to f of b1 and so on fbn. So majorizing if a majorizes b, then we have this inequality. And moreover, if moreover, actually, it is we have vice versa. If f if we consider moreover, if we have for all convex decreasing functions, we have this inequality, right? This inequality, then a majorizes b. It can be vice versa. You can actually, if this property we have for all convex decreasing functions, then we have then a has to be majorized. That just, I mean, like, so it is in some senses if and only if. Okay, how today I'm going to consider minimum energy, discrete energy, how it is related to how we can use it for minimum energy. Idea is the following. Let us consider a very general case. Suppose S can be any set, not necessarily finite, any set, and let rho be any function, symmetric function, right? On S cross S, this product of okay for and in this case, and let F let F be a real function. Let rho go. We send this rho like these pairs, like pairs of points in S, elements of this S, x and y, right? It's sent to D, some domain D in R, right? If you have some function f on D, that is a real function, that is a convex decreasing function, then we can define potential energy E sub f of x by very simple, just to consider for all pairs. We have f, we have rho, this is the real number, we can consider sum of f of rho xi and j for all pairs, non-ordered pairs. Yeah, this is the regular usual definition for potential and energy at F. Okay, what do we have now? We have a potential energy, right? We can also generalize, ask the following question, like a Thompson problem, to find if you have what is given S, set S, given rho, we have a rho, we have F, let us fix number of points, and to find all x such that gives subset S such that EF of x gives the minimum, attains its minimum for all element subset. Of course, it can be actually not exist, like it can be say, I mean, like not necessarily exist, but it can be an empty set. But it is just, I mean, we'll consider later necessarily a sufficient condition that it always exists, non-empty set. Okay, how to use this majorization theorem for potentials? It's very easy. I define by R sub rho of x. All this was all pairs. We have this row of all pairs. We have elements of the set, right? And we can consider all pairs and row of all pairs. So we obtain m choose two real numbers, and so we can compare. I mean, like now we can compare these numbers. If you have two m subsets x and y, then we can compare r of these two sequences of rows with this pair. Immediately, of course, you know, this modularization theorem, Karamat inequality, gives immediately implies the following theory. Let x and b be two m subsets of S. Suppose R sub rho of x majorizes R sub rho y, then energy EF of x is less or equal to EF of y. I mean, here I don't strictly convex. I mean, I consider like any convex decreasing function. So just like how we reduced this potential, we can consider modularization also for pairs of set of pairs of points elements. Sorry, I'm taking say points, but it is actually still not points. It's still elements of any set. Okay. Now I can define. It also can be. I can define some notation as a main. Actually, not so many definitions here in my talk. And let us consider M set. What does mean M set? M set. It is. We said that we consider all M point sets. Denoted by S to the M. I mean, that's all sets on points. And we said that X is M set if for any y for any y, it is either R of X majorizes R of Y, or they are incomparable. The same as we consider for real numbers, like majorizing, we have any the sequence is majorizes another one, like for y sequence, or just incomparable. We call the same set. And I denoted by M of S of rho of M. We denote all the set of all M sets of S of cardinality M. That's notation. And just one simple theorem follows from definition and follows from the modularization theorem that suppose we have rho, and suppose H is any convex increasing function, then M of S of rho belongs is a subset, or is a subset of M of S of H of rho. Yeah. So just we try to, if for a given rho, we can define many. We can other functions that is just H of rho. Composition of H and rho, right? And after that, we can consider also M set. We have this inclusion theorem, and let me just to give an example, our main example, what we are going to work. Actually, our main object is a sphere, in n-dimensional Euclidean space, unit sphere. Any sphere has two distances, actually. Now rho, I'm not going to consider now rho like only distance, but there are two distances. There's Euclidean distance and also angular distance. Here for any 2 points, right, we have distance. Of course, there are between the famous relation between angular distance and Euclidean distance. And now I just to for actually we can also put consider rho, right? And here we have for any real s, we consider different rho. Like we have said, just if you consider this r is actually Euclidean distance, r to the s for positive for positive s, for s0 it is just logarithm, and for s negative it is a minus r to the s for negative s. Yeah, it is. We have some spec. I mean, like we have different rho. It's of course from the previous theorem immediately implies this theorem that like if that inclusion that s is if s is less or less than t, then m set with rho equals rho s, be also m set with rho equals rho t. And also, this result, we have result about phi, about this angular distance phi. It is for any s less or equal to 1, we have also this inclusion. So with rho equals rho s, it is with s less or equal to 1, it is also will be m set for rho equals phi. Angular distance. Okay, so we have this different rho, and now let us consider some. We compare with functions. Namely, let us consider. We have now we consider a convex decreasing function as above, and we say that we define m sub f with respect to f, I mean m set with respect to f, is the following. Let us consider, suppose there exists infimum Vf, if infimum of energy for all m sets, right? And we say that x is the mf set if energy of discrete energy of x is exactly it's when it achieves its minimum. I mean, like this energy minimum. So now we have two kind sets for a given f. We have also mf sets, and we have m set, and we would like to and we would like to know when f set is a subset of m. Actually, I have also, it was some only when I in my first version of the paper, actually I had some it was incorrect. I mean, like I put some statement about that all mf sets are also m sets. Any mf set is also m set, but it's not correct. We need something, some additional assumption. I had some assumption, but it was not enough. Actually, it is possible to formulate it for any. I mean, this is abstract for any abstract set, but it's too many assumptions. There is very natural assumptions about this S set. Now it is, let first S be a topological space. We need compactness, a compact topological space is the first. Second, in this case, of course, rho has to be symmetric continuous function. Compact topological space, second continuous function. And the last assumption, f has to be strictly convex decreasing function, not just convex decreasing function, but strictly convex. If we have these three assumptions, topological space, we don't need metric, by the way, space, just topological space, and continuous, rho is continuous and strictly convex. This implies that any MF set has to be also M set. That means the theorem set in this general case, it doesn't matter if you consider M sets, right? It covers all minimum energy for any F. For any F strictly convex decreasing function. So in some sense, it is super minimum. I don't know, that it contains all of them, all minimums. Right. And for instance, the most popular potential in the sphere is the Riesz potential. I think everybody knows. I mean, what does mean Riesz potential? Let me repeat briefly. Usually here we use ES, but S already taken, so I can't use. Sorry about that. I'm using Riesz T energy. That means, this is a definition of what is the Riesz potential. It also can be defined for t equals 0, just logarithm, one of the distance, Euclidean distance. And there are several famous, like for instance, for t equals 0, it is also considered by for logarithm considered by Smale, the Simmons problem, and several others. Thomson problem is very popular. That is solved only for some particular case. For Thomson problem, it is this problem for t equals 5. And now, just to the main theorem, how compare? We already defined how compare minimums of Riesz potentials, like consider the set of all minimums of Riesz potential, right? For a given t, and how to which M set it belongs. Actually, the theorem, it is, of course, it is if you consider RT, it is of course works. But what is interesting, the theorem says actually all Riesz potential, if you consider minimums of Riesz potential for a given t greater or equal to 0, then it is belong for all S greater or equal negative, not only for t, but of course, we have a case of S equals t, but it is obvious. But actually, it is you can extend it even for negative t, right? So just that means we can play with rho. Yeah, this is our main theorem. Just so we try to reduce. We can reduce our if we can reduce consideration of minimum to Riesz potential and other potential to find the set of M sets on all S M sets. Okay, let us briefly. I have like 20 minutes. Let me maybe 5 minutes I will spend to discuss and to go to the F design. Otherwise, I have no. It's again I have no time to consider that. Okay. First of all, let us consider the classic case, namely, we consider the circle, unit circle, and we can discuss M set of angular for rho equals when rho is a angular distance. Rho is equal to 5. In this case, this M consists of regular polygons. Always consists of regular polygons. So not interesting, because we know that for most potential, it is for good potential, so it will be will be regular vertex of regular polygon. So this maybe not so interesting. But if you increase, but just I remain that in this case, when we have angular, that means we have this. It works only for s equals less or equal to 1. So we have this the same. This theorem implies that for rho equals R1, like for Euclidean distance, it is also consists of regular polygons. But if you consider squared distance, like R2, right? In this case, the answer is not so obvious. It's a complicated problem, by the way. For all m, I don't know a solution, but I know a solution only for the case for 4 points. Here we have it is will be one parametric family of solution, and here you can see this all this this side angular side angular with angular we have 2 pi minus 3 alpha 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 3 alpha, and the alpha between this 90 degrees and 120 degrees. So we have already something, right? Even for the case 4 points, we have some one parametric family. That means, however, we, for instance, it is a solution when our potential is a convex function on a squared distance squared, not with R, but it is the more weak assumption. In this case, we have we can have not only regular polygons, but it also some more exotic, some more complicated solution, like here. Of course, it's easy to construct this potential with this answer. The main theorem, one of the main theorem here is it is also I consider it regular simplex. The main theorem is the following: suppose S is less or equal to 2, S is less or equal to 2, and then the set of all M sets in this case in with n plus 1 points in n dimensions consist of regular simplices. I mean, that means we have, if you have a situation in two sphere in 3 dimensions, that we have 4 points. It will be regular tetrahedron, vertex of regular tetrahedron. Yeah, the proof is actually very close to use the positive definite properties. Yeah, and okay, it is some linear algebra, like it can be. It is not complicated, but it takes maybe, I don't know, like 5 lines, 10 lines. However, what is interesting that from one side, it is proved for S is less or equal to 2, but for angular distance, it is open problem. It is I have a conjecture about this how it looks like. I mean, all M set for with respect to rho equals when rho is an angular distance. It is actually, it will be 2 parametric family, like here conjecture. Just conjecture, right? And this conjecture is, let us consider tetrahedron such that its 2 sides are 2 opposite edges, AC and BG have the same length A, they equal length, and angle between them is theta. It is 2 parameters, A and A, where A between 0 and 1 over square root of 3, and theta between 0 and pi over 2. Theta greater than 0 and less or equal to pi over 2. In this case, my my conjecture that it will be describe all M sets for even for in 3 dimensions only for 4 points. It's a little bit strange, but I mean, like, it is not easy. But however, for that means, you know, this distance, I mean, like potential when we have rho equals this angular distance, it's more complicated. I don't know it is known or not, but it is like, so it is a simple open not simple, but it is open problem. I don't know how to solve analysis. Okay, let me skip some extension. It's some extension that is based on with restricted, but when we can say it's not all points and only with restrictions. Actually, I completely solved the question for 3-point set. For 3-point, when we have 3-point sets, right? Here give a theorem. Let me skip. But what is interesting, even for 3-point, we have a 3-point on the circle, right? The answer is not so obvious. We have for this number, like for s is less or equal to this number, right? We have a regular triangle. When s is between this number and the 4, we have a regular triangle, and some one parametric family. Yeah, and for s greater or equal to 4, we have also 2 regular triangles, and regular triangles always, you know, we have of course as a solution, but also we have some parametric family. But in this case, the difference between 2 and 3 just only we have here just smaller errors lies in the smaller interval, alpha in the smaller interval. So it is even in this case, yeah, we solve that, and but however, it is the answer is not 3, even for the case 3. For 4 points, I also considered that, and in this case, still open for s greater or equal to. Yeah, it is. We have a solution, but it is still open for s greater than 2. I show you some example for s equal to. It is solved, but for s greater than 2, it's still open. Extremely interesting case is 5-point set. You know that it was for 5-point set, and Peter is here, right? And the Peter spent I don't know how many years to consider this problem for 5-point set for, and the first result is it's about that. And is this what is known for 5-point set? It is known for with respect to angular set. We know it is already presented as a regular pentagon, and restricted also. Let me skip it. For 5-point set, also in dimension 4, of course, it will be regular simplex. But for what was the most interesting case, of course, it is open. Actually, you know what happened? Actually, I'm motivated by this case to find some solution for s positive s. I mean, like I tried to find this set. I have a conjecture. I had a conjecture. It will be 2 parametric. I thought that it will be 2 parametric family, like 2 intervals of orthogonal intervals, right? And as a North Pole, we have 1 interval, another orthogonal, another interval that orthogonal with okay. But it was a wrong conjecture. I spent several weeks, and after that, by computer, I found the counterexample. Now I think it is. I was so upset. I decided, okay, I forget about this 5-point problem, because the 5 problem. So people spend so much time before this. Because Richard Schwarzman proved it for cases s equals to 1 and 2, yeah, and now this extended actually It will be, but however, it is a triangular bipyramid in order to prove that. And now, okay, but my guess was okay. Maybe it is complicated for risk potential, but however, we can, when we consider M sets, it is 100% geometry, nothing more, right? More or less elementary geometry, understandable for high school students. It may be in this case I have something proof, but since I repeat, since it was a wrong conjecture, I could not actually I couldn't prove it. Maybe it is now. I think maybe it is complicated, even for three parametric set. Okay, but in any case, it is an extremely interesting problem, especially if you think that is how much time. Many. There are several attempts to prove it. Okay. What I have probably 10 minutes, a little bit, maybe a little bit less. Let me, and I'm again have more time to discuss in details F designs. It is related. It's also very natural to consider what I'm going to consider that F design that maybe look like very far from what we discussed before, but however it is very natural because it's my first application when I found first interesting first application. What is can be raw to have some minimum for T design. I will discuss later what does mean T design, and maybe to found some relation. And I found, okay, let us give a formal definition. Consider a set of M points in n dimension in dimensional sphere. I mean in Rn. And first of all, we define the moment Mk, the case moment of P. It is like it is a sum of we have all pairs of ordered pairs, sorry, of Eigenvalue polynomials of inner product of this pi dot pj with the points as our points. We consider that all the sum of Eigenvalue polynomials, and that calls it MO. What we know about the positive definite property of Eigenvalue polynomials implies that all moments are greater or equals to 0, right? It is the main property what we use in the Delsart methods and the linear problem now. But in general, we have this positive definite property. Also, it is considered for Eigenvalue polynomials also SDP, same definite programming also uses property. And so I defined moment, and definition is very consists of two parts. Definition. Suppose we have point we have m point set P, and let us consider all the set of all inner products pi dot pj. It's on inner product that the dot product of all points there, distant points, and let f can be any function, converted function. And actually, we don't need any constraints for fk. Can be any, not necessarily to be positive. And now, let us consider. And consider now, okay, it will consist of two parts. One, all if we have for this function, if the coefficient is not 0, fk is not 0, then they have to have mk of p equals 0. One. This all moments with non-zero coefficients are zeros, and the second, the set of inner products is a subset of zeros of function f. Yeah. Okay, both considered actually, both property considered. Like first one, it is famous T design, and T design actually is considered like in this case for all from from 1 till T, all moments are zeros, right? And also just one moment also considered, like I forget how it's called, that some also considered not necessarily to be all of them. Okay, this is a famous object already, I don't know, from 40 something years, beginning of started from the beginning of 70s. The second property is also known. Now it's still very popular because, for instance, if you have S distance set, right, with prescribed inner product. In this case, exactly, we have instead of zero, we can consider zero. But both properties known and considered that, right? And but when we put all together these two properties, we obtain something in some sense optimal set of points. Okay. Let me just to briefly explain. I explain several properties. First of all, how it is related to delta, how it is related to delta. About suppose we have a continuous function. Actually, you can think about polynomials because it's theoretically possible, but I don't know examples. I know examples. I know examples for minimum energies. Actually, there are some examples when we have no polynomial. Okay, anyway, but you can assume that f is a polynomial, and then if there for this for a given f, there exists f design in accordance with the definition. Then we have a design of cardinality m, then f of one is equal to m times f naught. F naught is the coefficient, f naught coefficient. You see that we have some, okay, it is explained, this two assumption, immediately implies this equality. That's exactly what do we have in Delsart bound. Look, pay attention that here we not assume that fk is a positive. It can be any, non-negative, sorry. But if you have, the theorem says, if you have additionally, we assume that fk is greater or equal to 0, is non-negative, and p is a such subset with such that it's in the set of inner products belongs to zeros of f. This condition, then, and the condition 2, then p is an f design if and only if f1 equals f naught. Yeah, it is interesting property because actually it's not necessarily to find, because it's not easy to check the moments, right? You have to know something about moments, Gamma polynomial. In this case, we don't need it. We just to check. If you have we check if you have some function. Check zeros of the function. Check also below if you have inner products belong to this set of zeros, and check this inequality because it's given for function. That we guarantee that this set is a f set. You don't need to check. I mean, like inequality. Okay. Maybe can I take 3 more minutes? Oh.
Yeah, that would be okay. Yeah.
Okay. Okay. Just let me just not to design. Actually, this the app design, that is why I mean, like I discussed it. Actually, all app designs are also M set with rho equals minus f of x minus f of x x dot y, or inner point of x and y. So with rho, with this rho, with rho is minus f. That is also property, and we can see that there is a strong relation between them, between this what we considered before and this. It looks like sometimes exotic, but however, for example, shows that it is okay. Especially there is some different families. For instance, universal codes. You know, the spherical codes. I mean, they give interest in them. Also, they exist very simple relation between T design. T already taken, so I denoted by tau design. It's Boy-Wallin confusion. Peter Boy-Wallin confusion always not T design, tau design. Yeah, it is also theorem. And if you have tau design, of course, it can, when it is P design, there is a property. What my last slide, what maybe is interesting, like it is also related to the seminar, is the following. Let us consider two distant set and F design. What is the relation between two distant set and F design? The first theorem set, more or less simple theorem, says that let us consider the quadratic polynomial t minus a times t minus b, and when a plus b is not 0. In this case, p is an F design if and only if p is a two distance to design. I mean, two distance to design, you know, that is one of the favorite case. No, it is, I mean, like, because it is actually related to strongly regular graphs. There is. So in this case, we know exactly what it is. It is also this object considered for many years. The case when b equals negative a, it is also a known case. It is so-called equiangular lines. But in this case, actually, still not. We still have, or I still not necessarily necessarily sufficient condition. Let me. We have here participant, by the way. Right. Actually, to consider it in the paper, where it is Burke. Yeah, we have here like in this paper actually consider this case equivalent lines and even more general. But Alexei Glazin told me that it's still there are some. It is not like completely solved. I mean, like it's not necessarily a sufficient condition about equivalent line. If b is not equal to negative 8, it's not equivalent, it's okay. But if for this case, still there are something to prove. Okay. So, oops, sorry. Yeah, and so this one of the open problem. I mean, the second problem is also it's very interesting because if you consider the following example, consider the regular simplex and the midpoints of edges that give us the maximum F design of degree 2. It can be proved. That for when a plus b greater than 0, it is gives us exactly n plus 1 choose 2. It is the upper bound for such two distant sets, right? For in any dimensions. And but question is, of course, the question is actually do we have general question is not necessarily to be F design. General question is, do we have other two distant sets with a plus b greater than 0 such that with this that attains upper bound. This I mean this of cardinality n+1 choose 2. But maybe okay, maybe this problem is very complicated. I don't know. We know this problem many years, but however, it's not big progress for that. But if you restricted by only F designs, can we prove that only it is unique, or just maybe I don't know, or maybe to find another one? And the last problem, it also for me it is very interesting. Actually, any graph can be embedded as any graph can be embedded to the sphere as two distant sets. I published paper, by the way, like yeah, 2 years ago probably, right? About this, about that, you know, even there is some more or less constructed, yeah, this one, yeah, about that. So question is, suppose for a given graph, can be embedded when graph can be embedded as a F design. I mean, we already have a graph, right? And can be embedded. We know, for instance, for strongly regular graph, you know that it can be embedded as a spherical F design. But what about other graphs? Do we have something? Do we have like there exist some examples? For instance, the Kissinger arrangement 4 dimensions, for instance, it is a F design. Yeah, also a design for some actually. But what about the general case? What we have to add? Okay, thank you. Sorry, that's really late. I'm finished.
Thank you very much, Oleg.
Mm-hmm.
Okay, any questions or comments from our audience?
I have a question. Some of it's just a bit of making sure that I'm understanding. So these M sets, were you saying that, is it always the case that the energy optimizing sets end up making M sets?
Yeah. Let us return later. It is very important. Let me turn to. Yeah. It is actually crucial question about relation between optimal set for energy minimizing sets and the M set. And here, look at this. Just a second. Yeah. Okay. The theorem says, this genius says, right? Suppose we have energy with the potential F is strictly convex, decreasing function, right? And the rho, but no, it depends on parameters. It depends on the set, right? Let us assume that it's sphere, right? As a sphere. And when we have a rho, some rho, it is continuous function. Then it is, in this case, actually doesn't matter with rho. There's only what we need from rho just to be continuous function. That's it, right? I mean, it's not necessarily to be distance any. In this case, minimum potential, energy minimum is the M set. It is just only solution, only one solution, only one constraint. F has to be strictly convex decreasing function. If it's not strictly convex, even on the circle, you can construct example, counterexample. But for strictly convex, if it's strictly convex, then then the minimum of energy is M settled, right? And moreover, like for each potential, I give you some stronger theorem about that. For I describe actually all I mean this row can be described. It's not only that one, but actually for other row it also can be. Like we have some potential because the main idea has to be strictly but it's
Okay, so then I guess that my follow-up question is, have you come across instances where it's easier to characterize all M sets than it is to determine minimizers of an energy?
Actually no.
Okay.
Yeah, of course it is, you know, we cannot tools. Right? When I started consider F design, because we have no tools. We have a definition, understandable for high school students, right? We have geometry. Let's consider like S2, right? Right? And very simple question, even simple question about like how they which set majorizes another one, right? Even let's consider like Euclidean distance, say, for simplicity.
Right.
Right. And it is complicated because it is, for me it is not clear. I just to look in all these books about majorizing, like there are many papers and books even, but however it is some I couldn't find any tools for that, right? So that is why just I found some simple answer, right? Like circle or some like a simplex with a number of points and small one, right? But I show you that even for 3 points there are some non-trivial. Actually, it is open, like everything open. But I hope that if you have a good family, okay, if you consider this 5-point problem, right? I mean, in this case, maybe if you found some family, say three parametric family, maybe they exist if you good conjecture, right? Maybe we can prove. In this case, all problems will be can be 5 problems can be solved very easy because we have even 3 parametric family. Might have some conjecture, but it is I'm not sure that it's true or not because I'm just left this problem immediately when I found the counterexample. It was several years ago. Yeah, 3 years ago probably. And if you found, and maybe I can assume even some elementary solution of this problem, right? If you have elementary solution, that immediately implies, I mean, this solution of this problem. But however, I don't know, no tools, because how you compare 2 sequences of distances, right? You can compare, but because it is I mean, the definition, majorization not so easy to see. So just only like unfortunately, I think I say no. I have no. Actually, I don't know how to work with that. Even for using computer, you know, like numerate. I've also tried. It's also not so easy. It's not obvious how to do it. I could. I just actually I tried to find like some random walk. I mean, like using this algorithm. I found this counterexample. Yeah. Even dimension not big, right? In the for 5 points, a dimension only seven dimensions. But however, when I tried to do that, you know, like look at the different configurations, right? It is no, I don't know. I mean, like no algorithm how to find the minimum. This function is good. Everything is like it is. We can do it for function numerically, but not for M set.
Okay. Thank you.
So it's a sad news. I know that. But for app design, I mean, it's another story. For app design, they have tools, they have everything, many publications, yeah, many examples. It's another story.
Yeah, so it seems in most cases these M sets are going to be to depend on some number of parameters. So in other words, you mostly don't expect them to be, finite or anything like that. They're mostly cardinality of continuum. And then
Yeah.
I guess in this light, a reasonable question maybe to ask would be, okay, let's say the underlying set, I guess maybe you denoted it by S or something, right? The compact set is convex, it's compact, and so on. Can you show that for some f, well, for some distance you'll have a discrete M set? Like, do you expect that this ever happens?
No, we have okay. You mean no, because we have discrete, we have unique up to isometry. For instance, like this case, right? Regular simplex we have, but it is not. It is just if you consider the set up to isometry, in this case it's just unique.
No, right.
Just, it is discrete one, but all my other examples, we have a continuous. I mean, like continuum, right? I mean, many, like in more or less some.
Yeah, non-isometric. Yeah.
Yeah. Yeah, but for all other cases, we have some family. I mean, like some manifold, submanifold in the configuration space. Yeah. I mean, the same sets. So I don't know. I like I show you for yes, like for instance, like in this case, right? We have we have some family even for 3 points on a circle, right? And for 4 points, and I show you the example. It's conjectural only. For angular distance, we have this some special case of two parametric special case of tetrahedron, also two parametric. It is probably it can be solved. Maybe expect it is will be extremely interesting, right? If you have some isolated also discrete set like spectrum, right? Let's say. No idea. Actually, no idea. It's very complicated, right? I know the question. It's about how can characterize, how can. No, you probably it is not complicated to prove that it's a compact. It is probably okay, right? Because it falls. If you can compact space, it is the full problem. Maybe it is true, but however, okay, compact, but even about dimension, right?
Yeah, dimension is not clear at all. Yeah, what's the degree of this? Yeah.
Yeah. So yeah, but it is, of course, it is interesting, right? Because even for dimension, because we try to realize what is can be what we are going to describe. We are going to describe all minimums, all
functions. Yeah.
Yeah, it is very strange, right? I mean, like it can be. Or how you can do that just to find. Actually, I also use this method. Try to find examples for some given potentials. Okay, let's think about these 5 points, right? We have bipyramids, right? Triangular bipyramids, and also we have some for when s greater than 15 something, right? We have this pyramid, square pyramid, right? You remember, you know this case, right? It is actually, it will be one parametric family, by the way, if you know that, right? It's definitely for 5 points we have at least the dimension is at least one.
At least one, yep.
Yeah, but it's my guess now it is 3. Maybe not. I don't know. But it cannot be something very complicated on one side. But I don't know how to prove it. I don't know. It can be something, some family, some geometric family. It's only 5 points. That is very yeah. That is very attractive because when I think, okay, it is a geometry, but we have to describe some some polyhedra. I don't know, some manifold of dimension 2, 3 in configuration space, but I don't know. It still looks like very complicated.
But you can call them not only M set, you can call them a universally optimal set.
No, it's not me. It is universally optimal. It is called by Henry Kohn and Kumar.
Well, right. It has different meaning, but yours are universally optimal in a stronger sense, even, right? So for marketing purposes, you can refer to these as universally optimal sets.
But no, you already taken, already used this.
Well, yours is even better. Generalized universally.
Universal optimal modularization set. I thought so, because M came from modularization, right? But people actually confused about modularization, because modularization means we have like so something like something minimum, right? It is some okay. I don't know. It is interesting. I mean, to how to find a good name for that. But in something, yeah, you're right. Of course, it's a universally minimum, maybe. I don't know, universal minimum, like set of all minimums. Yeah. But I don't know what about tools. It is very interesting. Maybe my first hope when I think about this, okay, this problem, this 5-point problem, will be solved very easy, because we describe this family, right, and all M sets, and after that it will be like very easy to prove it. But not. That is why.
Okay, let's see. Any more comments, questions? Okay.
I see like,
so,
there's Lёша, I see Glazir and such. Hi, everyone. Yeah.
I guess I'll stop the recording.
Yeah, let's stop the recording. Then